Good afternoon, great hopes. Welcome to you once again to our Smart Caps lessons, proudly sponsored by VT Africa Holdings, as well as the Basic Education Department and other. Well, we want to welcome you back. We trust that you are warming up to the heat of the exam, not to scare you, but it's a very crucial moment that you need to have slightly of some sleepless nights and study, especially on mathematics. You cannot fall asleep when you are doing maths. It's very much of what we can say. It's going to raise you up. You can do so much more. So with that in mind, we will be having our class today, which will be on calculus. And we are going to begin to look at what is calculus, what is your grade, and what is your first principles. Along with that, we'll be inviting you to be part of our assessment, which will be accessible if you go to www.hellosmart.com. And you can sign up as a guest, and you put the ID number on the board, which is 598751. So you're gonna just put that in, and you add your name, and then you are smart and connected. So we have a wonderful time in this session, and we would want to have you understand better what your calculus can do and how you can pass this in your final exam. With that, let's go right into the mix of things. And we are looking at the topic of differential calculus. So according to your ATP, this would have been in term 2. But as you know that grade 12, we are sort of on the race in terms of time. So the terms don't really matter in this case. It's more about covering stuff that are important for your final exam. And so as we start on this, you can just be looking to be able to know what is your calculus and what it can do and the limits and the first principles. Okay, some of the items that you also cover, as I've mentioned, we'll also deal with where does calculus really come from, and that will be answered in terms of gradient. We also have limits, and by limit, we simply mean a number such that the value of a given function remains arbitrarily close to that number when the independent variable is sufficiently close to a specified or sufficiently large. For example, so I guess that you are picking the parts that are important. So it must be sufficiently close to a specified number or point, or to be sufficiently large. For example, the limit of 1 over x is, because as x grows to infinity, the limit, you have now the limit become smaller, which will be 0. And also the limit of x minus 1 squared is as x approaches 1. So you can see that if you had to put where there is x, then that would give you 0. So by not putting 0 directly, putting values that are close to 0, you see that this particular expression will approach 0. A limit is used to approximate the rate of change or gradient of a function at a point. So there are many examples where we use limits, and limiting factors in terms of mathematics, we are talking of that particular point where a certain variable or value is tending towards. And you will see that these are used a lot in our science, in our finances, to know or to extrapolate what certain values will be without necessarily going there, but knowing that it means if we take time, we can reach that particular point. So arguments have been put in different riddles that if you have a 1 liter, for example, and then you want to divide it into half, and then you divide that half into a quarter, and that quarter into another half, and that, you continue on and on. You can see that you can never finish this water that is in the container, so it will go on and on. We call that infinity. So an argument could be put that, so it means the water is more than 1 liter if you are able to keep pouring it, half of it. So this kind of riddle, which might look to be sensible, that we can put infinite number of cups as long as you're putting half of the half. I mean, to the last drop going on, we will not finish it because it will be half of the previous. And you can see that such a question can be disrupted by us showing that no, see, our container was 1 liter, all these must add up to that 1 liter. There's no way that it can just go to infinity without any kind of checks. So you can begin to show it that this would eventually go to your 1 liter. So this 1 liter will now be the limit where it's going, even as you are adding. So all the additions that you have from here, they will give you the 1 liter. Okay, so finance use a lot of limits to just know what will happen to your rate of interest and all that, given time and how much maybe your money can get to be finished if maybe you are paying a certain amount every time like that. So all those things come in very handy in different scenarios. Now, here is a mathematical worked example. We want to find the limit as x tends to 4 of x minus 16 over x minus 4. So you might be very disturbed by this and think that it's something that can cause you a heart failure or something, but this expression can be made much simpler by simply factorizing it. Remember, we just did our polynomials where we factor, and when you factorize the top part, you will get x minus 4, x plus 4 in brackets, which can easily cancel with one of these in the denominator. So eventually your expression was much simpler. It's actually a linear expression, just x plus 4. So when we write it like this, limit as x tends to 4, we can actually substitute the form in this result. So when that we put a 4 here, it will give us 4 plus 4, which is 8. So it means the limit of that expression is equals to 8 by calculation. Okay, so that's a good introduction of some of the things that we'll be doing. But first, let's start by looking at where does calculus come from. We don't want to be teaching you things that you think, but where will I use this, or where are we coming from, where these things are discovered by some Martian people from Mars or what? These are very practical aspects that we use in life. With calculus, we were able to do a lot of mechanics, and as I said, some finance, and almost most studies are hinged on calculus. And calculus was actually discovered by Newton, one of the scientists using calculus, you are able to understand things better. You can think of what will happen without necessarily doing it. So it helps us to already simulate things and look beyond what we are seeing to extrapolate results that are not yet measured. So this is how it came about. Newton was looking at what we call gradient of a symbol curves. And in the process, we can just tell you that gradient simply means slope. And by slope, we mean that how you are changing as you go up, the change in x and the change in y. Gradient can be that or that. So imagine you are climbing up a mountain, and if you are walking there, you will see that you need to add energy here in order to climb. So you need to climb, you need to add your, but here we will take it that you don't need to add any extra energy than your normal walking on this part. So there's then on this part where you're going downhill, you actually are being pushed to fall down, isn't it? So you actually getting the energy to move. So we call that slope to be negative. So in essence, slope is read from left to right. So some students confuse. They start to think that what about the, what if you are going down on this first one? So slope is made left to right, left to right, left to right. So if you are going up from left to right, your gradient is positive. If it's just a straight horizontal line, gradient is 0. And if it's actually going downwards, then gradient is negative. So that's some basic important things you need to be aware of. So here is where we get our gradient formula that you are very familiar with, I'm sure, that the average gradient on a curve can be calculated by connecting 2 points on and using simple analytic method to calculate that gradient. So as can be seen in the diagram, the average gradient of the graph is continuously changing because at any point your gradient, if it was here, your gradient would be that. So when you're putting gradient, you actually should just touch the line, the curve on one point. And it can be difficult on a straight part of a line. So you need a ruler there, and so that you don't make such a bend like that. So I'm just illustrating to you how you can actually get the gradient. But the gradient I've already illustrated in black with a ruler, which is a straight. That the gradient from A to B is actually less in value than the gradient from A to C. In other words, A to C is more steeper. You have to climb more. You have to put more energy to go up the slope. To do that, then you would need on A, B. So if you are climbing from A going to B, you can see that the energy you put is less than the one that you'd use from A to C, not in terms of distance, but in terms of the incline of things there. So if you are a mountaineer, people who climb mountains, they would know what a slope is. And anyone who is able to drive, you also know that when you are driving and you reach a place where you have to go uphill, you put more on your accelerator. So you put more fuel there because it's need to climb. But when you're on a straight path, you don't need to put much of anything. When you are this side on a slope going down, you actually need to put your brake. Don't put any fuel because you are going down. So that's how your gradient is visualized. Now, an important formula that we learned in grade 10 was that gradient is equals to change in y over change in x, which change in y can be put down as y2 minus y1 all over x2 minus x1. So this would give you your gradient. Here is something that you can have a feel. What is the average gradient between point A and B on the graph? And my hint is that your average gradient, which we usually use the letter M. So gradient could have been used the letter G for gradient, but science had already taken G to represent some gravitational cost. So we ended up saying that M could represent gravity because X has been used so many places, in maths, Y has been used so many places, and Z for the Cartesian planes, and other letters like that. So M seemed to be vacant, available. And so you remember your gradient formula is Y1 over X2 minus X1. So it comes like this. And by we simply mean that you can substitute different values on Y and also on X. If you want to be strict with it, according to this particular question, you can also write it Y and call it. So let's say this is our A and this is our B. You can also say B minus YA over XB minus XA. The important aspect here is to look out not to mix your A and B or your 1 and if you start B, make sure that on the denominator you also start with B. If you start with A, make sure that on the denominator you also start with the same A. So this would still give you the same answer, even if I exchange them, but I have to make sure that my X is complete. Don't half exchange. You must make sure that if you are starting A, you are starting with A on the numerator and denominator. If you are starting with B, you are starting with B on the numerator and denominator. The same applies if you also have Y1, Y2, X2, and X1. So anyway, to get to our result, we need to know what is the coordinate at B. So B coordinate seems to be at 4. So the 4 is easy to figure out. So 4 from the x, and then 1 from the y. All right. Then what about a? A is clearly at 2 on the x, but at minus 3 on the y. Because of the scale, we are having something like 1 here, 3 here, 5 here, 1, 3, minus 1, minus 3. So hence we come up with this. And so by simply substituting in this formula that we just discussed, you start with your y values. So your y's are that, your x is this. This is your x, this is your y. But the formula starts with y. So you will say, for example, that all over. So I started with the y, now I go to the x. I must make sure if I started with 1, I must start with, so 4 minus 2. So this can give you a result such as, so I'll just show you below here. So if you calculate this properly, the top one is merely adding because minus minus is a plus. So you do have 4, and on the bottom we have 2. So the result is a 2 because it's 4 over 2. And that seems to be our answer at A, if we are looking at the average gradient. Okay. If I might review the answer, you would see that it's indeed A, which is that. Okay. So one key point to mention before we leave this is that we were looking at average gradient. So the gradient, as we already said on a previous page, was that the gradient is changing each month. So I even illustrated it there. If you were to draw the gradient, you will see that it's changing a lot. It's changing a lot. It's changing a lot. But at that point between A and B, the average gradient would be 2 because you are simply looking at those 2 points. Okay. So on the coming question, we would want to see more of your participation on the assessment for those who are on the device. So you need to be logged in. Remember, you're logging in. You simply go to hellosmart.com and then you put your sign up ID number, which is 59875. You see that there at Freddy, you'll be able to already access our assessment. Okay. So all things being fine, we would want to check another scenario. So let's look at the gradient at a point on the curve. Okay. So the gradient at a point on a curve can be calculated by drawing a tangent. So a tangent is simply this line that we've been drawing. So that's a tangent. So a tangent simply means a line that touches the curve at one point, and it's sort of, you must make sure that it's kind of symmetrical, this side and this side, so that you will be able to measure things correctly. So the gradient at any point on the curve can be calculated using the method of differentiation first principles. So when you differentiate by first principles, you will simply be using that idea of the gradient, but putting it in a form. But for now, calculate the gradient of a point that is given A. So the point is there, A. So what you could do, you have various ways to try and get this. You could also use this tangent to say, I want to look for any 2 points where my tangent is touching. And so maybe you look for a point such as that. So your line is sort of on this point, and you look for another point where it's touching. So maybe here. It will be good to choose a point. The line is actually touching on the corner of the boxes. Okay, so that's how you can actually do it. So you can choose any type of line part of it. You can choose any line, any part, and then any 2 points, you use them to find your gradient. So remember, your gradient will come from y2 minus y over x2 minus x1. So if you are slightly accurate, if this was my point number, I'll just say PQ. So if this is PQ, I can change my 1 and 2 into PQ like that. But eventually you need to talk about what is the value of that X value and Y value. So somewhere along that, you're gonna end up with something like y2, which is going to give you, say, at q, your y is 2 minus, then your x on the other hand, if this is 5, this one in between is like 4 point. So this is x on that, so it's 4.5. So that's just your q here. Then you also do the same thing with your x. So if you chose the point at P, according to what I chose there, my point is roughly on -2 on y, this point, and x is slightly above 3. So x is slightly above 3. It can be, say, 3.1 or 3.2, like that. Okay. So if you calculate this to an answer, but your answer should have sort of some decimal places, because are not exactly hammered onto the corner of the blocks. So I believe that this, and yes, our solution here shown would be B, and because those decimals are because our points are on the given box corners like that, so you have to measure, you have to approximate slightly. Hence, I put the 3.2 like that. Okay. So this will be very interesting to actually be calculating all these things like this. But let's now check another method that can make life slightly easier. as we are exploring the different approaches to this wonderful topic of calculus. So I would want to mention it that calculus is one of the most educated topics that you are doing in your, and just the sound of it to tell your peers that you are doing calculus should give you quite a bit of excitement, and it is very useful, like I said, in your finance, in your engineering. It's a very grand topic. So we are going to now differentiate by first principles. And what do we mean by this? We are going to simply use this formula. So this will be our formula to use whenever we talk first principles. So just to check the formula slightly, we will see that the formula says f prime of x, which simply means that differentiation of x is given by the limit as h tends to 0 of x plus h minus f of x all over h. So h is an arbitrarily chosen letter again, like we mentioned. So it simply means a slight deviation from your x value. So we use this to get to our limit as the function is actually a gradient function. So one of the things I want to mention is that whenever you hear the word gradient, just think of differentiating. The moment you hear the word differentiate or differentiation, just think of differentiating. The moment you hear the word tangent in this topic, you must just think of differentiation. We'll show you a couple or two other terms as we go that simply mean differentiate, because sometimes the English of it trips us down when we don't know that here we are supposed to simply differentiate and get to the final where we get good marks. So these are synonyms, I might crudely say, that they simply need you to differentiate. Okay. And then, so if we are to calculate or to work this one from first principles, how are we gonna do that? So we can do this by simply employing the same formula that we had. And that formula was to say f prime of x is equals to the limit as h tends to 0 of f of x plus h minus f of x all from, so let's move this one. So all this is over h. Okay. All right, so all this over h like that. So I just had to write it so that you remember where this is coming from. So our f of x is this. Then there's somewhere where we need this on that formula, as you can see. So what it means, we are going to our f of x, and then wherever there is x, we put x plus h. Then where there is a 4, there is no x, so we simply remain with our 4. So it will end up with this. And then since there is a squared, we expand and to that final result. This is part, some learners like to do this so that you have already sort of partly solved it to make the problem easier. So you've already found your f of x plus h that you are going now to put. Oh, so yes, I actually written this here. So you are going now to put this into this formula, and so you put that f of x plus h, and then you also subtract the same f of x all over h. Okay, this is all divided by h, and it's a matter of simplifying. Like here, you look for like terms, you end up with this, and then you also check how you can make it much simpler. You can even factorize, like in this case, and then you divide by your h. So when you're at this stage where you have just your 4x plus 2h, you now tell yourself that but h is going towards 0. So this means I can make h 0, and so you remain with that result. F prime of x equals to 4x. So f prime of x simply means the differentiation, the first differential. So that is the same as later on when you are using dy dx. So this is the same as that. It simply means the differentiation of x with respect. So we are differentiating y with respect to x, or the whole function with respect to x. Okay, and so another worked example for you comes up. Determine the first differential from first principle. So again, this might look scary. I can, in some instances where your x is in the denominator like this, but nothing to be scared about. This is simply this very same approach. So you simply look at your x and all that. So you still have your, what is f of x plus h. So when you do that, it's advisable to do that, because if you do it at once, some learners might make mistake with the subtraction sometimes. So it's better to first simplify this f of x plus h separately, then you marry it together in that formula of the first derivative. Okay, so in this case, we are going to end up with just the right thing here. So our f of x plus h will come out like this, because where there's x, we are simply going to add an h. Then we can make it slightly into another form by using a common denominator, and we get to that stage. Then finally, we can remove the brackets, because we are usually expanding when you are finding these derivatives. So your syllabus allows you to easily differentiate when things are already in expanded form, rather than when it's factorized, which would be your first year at university, where you use the product. But at this point, you want things to be expanded together without brackets, so that you can easily differentiate. And when you differentiate, you're going to be looking at this, but you are going to put it into that formula now, where it will have to do with the rest of the. So remember, our formula is there on top on this page, and so we are going to put our f of x plus h minus f of x, and then all this over h. And then you see that it looks quite messy in a way, but there is a light at the end of the tunnel, in the sense that you can simply use your basic mathematics here to say that a denominator that are here in this point can be pulled down to be a denominator down here. So you need to have those skills to know that such a denominator of this. So you first look for the common denominator of these two, and then whatever denominator you get, then you pull it down also as part of this. So I believe that you still have your h at that stage. So somewhere you still have your h. So your h is like still there. And as you can see on the next line, the h, I brought it back here. And you can simplify this to make it a bit to look a bit nicer by simply simplifying things together. You see your h is now part of this denominator, and then you have on top you had just minus h. So you factorize your h on the denominator as well, and you divide by that h, and you put your 0 on the h. So your resultant answer would be that minus 1 over x squared. So this might look cumbersome, but it's something that is a matter of following stages or steps that are just sequential. And you use your fractions to know that there's a common denominator. You use your factorization at some stage to bring out the h to cancel it. And you also end up applying the limit, which h is tending to 0, most likely in most cases. And then you take your h to be 0 and you get to your answer. So very interesting approaches to your calculus. So here is your 10 to use the first principles to calculate the first derivative of 3x squared plus 7. So you are using first principles. Some learners are very educated. They cheat by simply using the formula here to say that I already know what is dy dx, so this will give me this and that. You mustn't do that, because in that case, there are marks that are being given for each of these stages. You can see how much work was in working out this. We started on this first, we went to second page, and we went to third page to get to our final. So you cannot simply get all these marks by doing a shortcut, which is rather very smart, but we're gonna use that on other instances. But the moment your question says first principles, tell yourself that you need about 5 minutes to work that particular question and do it correctly. Put your formula down and do the part working and get to your final answer. So that's the gist of the matter here. And so have a look at this particular scenario we are here and check it. So those who are on the gadgets, you have to work out and choose your solution, whether it's A, B, C, or D. We don't usually have so much of multiple choice in math, and so you are likely to you have to show you're working in a exam setup. So you would need to actually have your work and all that. Okay. So look at it. Even if you are using your paper or handbook, you can work on that using first principles. And that would be a point to stop. And we want to appreciate how that we've already started to look at the various aspects of calculus. In this case, our differentiation, the gradient function and tangent, which things we made them together in the end to solve any question that comes around these cases. So have a look at this and work out from first principles this particular question, and also needing you to check what will be the result of the first principles when applied to this question. So do look at these two questions. You can simply write them down and then you calculate what is the first principles of this one and the next question.